All right, before we move on, I want to talk about number 12, modified. This is a what-if scenario. You'll notice that in the couple of examples, all the examples we've done really of substitution so far, when we let u equal this expression, so this is the same problem as number 12, except I've adjusted this. Now this is negative 32x instead of negative 8x. When we let u equal to this expression, always before, when we found the differential, why, what a nice coincidence. It matched up precisely with what we had left over. What we now consider is a more common circumstance, which is it doesn't match up precisely. And so we start down the same path. Well, first off, we're going to rewrite this, right? Rewrite to get rid of the radical. So this is simply rewrite. There is no calculus taking place here. 3 minus 4x to the second to the 1/3 power. And this is still times negative 32x dx. Now, everything needs to get translated into the u language. I'm going to move this over here to the side just a little bit so I have a little more space. Let u equal, using the same principles as before. It's the quantity being raised to a power. It's the function being acted on by another function. It's the larger of the two degrees. By all those bells ring to say let u equal 3 minus 4x to the second. Now, we need to find the differential and account for everything that's up here. What we have so far, that piece is accounted for here. How do you say 3 minus 4x squared in the u language? Translate that. That translates as u. So this is going to become, when we substitute, u to the 1/3. That part's straightforward. What now is left to be translated? What is left unaccounted for is that piece. Whatever is unaccounted for after this let statement, that is the piece you need to create down here at the lower right. Here's how that process is done. It's a matter of technique. It's absolutely technique. Do the same as before. The differential with respect, or the derivative with respect to u on the left, the derivative with respect to x on the right, and the derivative here is negative 8x. This, in the previous work, in all the previous work, whatever we got from this derivative, why, wasn't that nice and coincidental? It matched up with what we had. But here, notice, it does not match. Here's how to handle that. What you may do with this line, you may, if you wish, or if as needed, you may multiply both sides of this equation by the same non-zero constant. Any non-zero constant you like. If you wanted to, if for whatever reason you wanted to, you could multiply both sides of this equation by 50, or by negative 9, or by 128. Anything you want, you can multiply both sides of this equation by any non-zero value. Now, you may not multiply by different values. You may not multiply this side by, let's say, 4, and you may multiply this side by 10. You may not multiply by negative 3 and 6, or 1/2 and 3. You may not multiply by different values. You may not. Students try this all the time. Not all the time. Students try this frequently. Every time it's wrong. It is wrong. You may not multiply both sides of this equation by a variable. If this says x to the second, and you try to multiply both sides by x to create x to the second, that is wrong, because when you multiply this side by x and this side by x, you will create x du, and now you have scrambled the language. Everything on this side must be in the u language, everything on this side must be in the x language, and you may not cross the wires. You may not multiply both sides of the equation by a variable. However, what we may do is what we're going to be after. Multiply by the same non-zero constant. Look at what you have, negative 8. Look at what you need, negative 32. And you supply the multiplier that makes that happen. The multiplier is pretty clear, it needs to be 4. So multiply left-hand side by 4 du. Multiply the right-hand side by 4, negative 32x dx. And now, the substitution is exact because you have created precisely this leftover bit. This part has now been accounted for. This piece is accounted for by u. This piece is accounted for by 4 du. So now the question is, how do you translate this expression into the u language? Integral of. This translates as u. So instead of garbage to the 1/3, this is u to the 1/3. And instead of all this mess, negative 32x dx, how do you translate that into the u language? That translates as 4 du. Now the question is, what do you do with the 4? You may really multiply anywhere you like. Usually, and this is typically the simpler version, you may multiply inside by 4, outside by 4. Usually, I just throw the multiplier, and most people typically throw this multiplier out front of the integral. And just remember that constant multipliers multiply along. It's just going to multiply along, and then when we get our final result, you can simplify if you like. So, blah, blah, blah. That translates as 4 du. Now, we've substituted everything. We've translated this into the u language, and we have created a basic form. So this is now the antiderivative. Constant multiplier multiplies along. This is u to the 1/3 plus 1 is 4/3. Divide by 4/3 means multiply by 3/4 plus the constant. And now you back substitute to go back to the original language. You don't really need to do this, but it's probably not asking too much to see that those 4's cancel. And so it's probably not too much to say let those cancel. And so then if we go back to the x language, instead of 3u to the 4/3, it's 3 times this to the 4/3. So this is 3 times expression to the 4/3 plus constant. And we're out. So we'll go through several examples of this procedure to make sure you have that worked and have that sort of down in your mind. And if you can take this forward into Calc 2, you'll have a leg up on everyone else you'll be working with.